Have you ever been watching a huge live event online, maybe a company-wide meeting or a major game, and just wondered how the internet doesn't completely buckle under the strain? Well, today, we're going to pull back the curtain on network multicast. It's the unsung hero that makes all of that massive, simultaneous streaming actually possible. All right, let's get into it. So here's what we're going to cover. First, we'll look at the problem, what I like to call the network traffic jam. Then we'll introduce multicast as the smart solution. After that, we'll break down the key protocols that make it all work, IGMP and PIM. We'll see how the whole thing gets optimized, and then we'll wrap up by talking about why any of this really matters in the real world.
All right, let's start with the problem itself. How is it possible for one single video stream to bring a super fast, expensive corporate network to its knees?
I mean, we've all been there, haven't we? The CEO starts a live all-hands meeting, and suddenly everything else you're doing just slows to a crawl. The reason this happens all comes down to how data has traditionally been sent across a network. You see, there are two, let's call them brute force ways to deliver that stream. First, you've got Unicast. Think of this like making 100 separate phone calls to tell 100 people the exact same story. The server has to send a unique, identical copy of the stream to every single viewer. As you can imagine, that eats up bandwidth like crazy. The other way is broadcast. This is like shouting on a loudspeaker in a packed office. The message goes to everyone, whether they want to hear it or not. This forces every single device on the network, yeah, even the printer in the corner, to process that data and then throw it away. Both methods are just wildly inefficient. And this is where our hero, Multicast, finally enters the picture. It gives us this really elegant and intelligent third option that completely avoids the problems of those other two. You know, the best way to think about it is like a conference call. The speaker just talks once, and the phone system is smart enough to only connect the people who've actually dialed in to listen. With multicast, the network itself does the heavy lifting. It sends a single stream, and that stream only gets copied at the very last second when it needs to split off to reach people who actually want it. So the really crucial point to get is this. With multicast, the sender sends the data just one time. The network itself is intelligent enough to copy that data, but, and this is the key, only at the intersections or routers that lead to someone who has specifically asked for it. That means no wasted bandwidth and no bothering devices that couldn't care less. Okay, but how does the network know who's interested in the first place? Well, that's where our first key protocol comes into play. It's called IGMP, and it's basically how your device raises its hand and says, "Me, please." IGMP stands for Internet Group Management Protocol, but you can just think of it as the network's subscribe button. When you hit play on a live stream, your computer uses IGMP to tell the router it's connected to, "Hey, I'd like to get the stream for this specific multicast group." It's kind of like telling your TV you want to watch a certain channel. And the process itself is just a simple three-step handshake. First, your device sends out an IGMP join message. Then the local router gets it and makes a little note. Okay, someone on this part of the network wants that stream. And boom, just like that, the router starts sending the data down that specific wire. If nobody on a part of the network asks for it, the router just doesn't send it there. Simple as that. Okay, so IGMP takes care of things locally on your little segment of the network. But how does this stream get from a server halfway across the country all the way to your local router? For that, the network needs a kind of GPS system, and that system is a protocol called PIM. PIM, or Protocol Independent Multicast, is the language routers use to talk to each other to build the most efficient delivery routes possible. These routes are often called distribution trees, and they create this logical map that guides the stream from the source to every single subscriber with absolutely no wasted steps. Now here's where it gets really clever. PIM actually has two main flavors. The first is dense mode. It works on the assumption that pretty much everybody on the network wants the stream. So it just floods the traffic everywhere and then cuts back or prunes the paths where nobody is listening. As you can probably guess, that's not very efficient. Sparse mode does the exact opposite. It assumes very few people want the stream, so it's an opt-in model. It only builds a path to a router if that router has explicitly said, "Hey, someone down here wants the data." For that very reason, sparse mode is the standard for just about every modern network out there. So, we've got our subscribers and we've got our routes. But the real magic of multicast, the part that makes it so powerful, is how the network is constantly, automatically optimizing these routes to be as efficient as they can possibly be. A lot of this optimization involves two different types of these delivery trees. First, the network builds what's called a rendezvous point tree, or RPT. Think of the rendezvous point as a central meeting place. It's a really fast way to get everyone connected and start the stream flowing quickly. But once that's up and running, the network switches to a shortest path tree, or SPT. This new tree creates the most direct, optimized path from the source straight to the receiver, cutting out the middleman and giving you the lowest possible delay. And this just perfectly shows the self-optimizing nature of Multicast. It's brilliant. It prioritizes speed at the very beginning to get you connected, but then it switches gears to prioritize efficiency and give you the best performance for the long haul. It's a dynamic, intelligent process that's happening completely behind the scenes. The network also has to be good at cleaning up after itself. So when the last person on a network segment closes a stream, their router sends a prune message up the line. This basically tells the rest of the network, hey, nobody is watching down here anymore, and this effectively snips a dead branch off the tree, saving all that bandwidth. And of course, the opposite is true too. If someone new joins on a branch that had been pruned, their router sends what's called a graft message. This reattaches the branch to the delivery tree, and the stream starts flowing again almost instantly. This constant cycle of pruning and grafting is what keeps the delivery tree perfectly lean and efficient at all times. Okay, so we've definitely waded through some pretty technical stuff. But what is the actual real-world impact of all this clever optimization? Why should we care so much about this? Well, it really boils down to this one incredibly powerful number. With optimized multicast, each link in the network, each cable between routers, only ever has to carry a single copy of the stream. It doesn't matter if there are 10 viewers, 1,000 viewers, or 100,000 viewers downstream. Just one copy per link. That's the core of its incredible efficiency. And that efficiency translates directly into the things we rely on every day. It means we get stable, high-quality video for those big corporate events. It means our expensive, long-distance network links don't get totally saturated. It provides the super low latency that's absolutely critical for things like real-time financial data feeds. And it reduces a strain on all the routers and switches that have to power the whole system. And really, this is the bottom line. When it's set up right, multicast is a phenomenal solution. But without these critical optimization protocols like IGMP and PIM, it can actually flip around and become the problem itself, acting more like an old-school broadcast and flooding the very network it was meant to save. It's a great reminder that behind every smooth video stream, behind every instant data update, there is this complex, elegant, and often invisible system working tirelessly. It really makes you wonder, doesn't it? What other hidden systems are humming along right now just to keep our digital world running seamlessly?